Hello, am I audible?
Yes, sir.
Yes, sir.
Okay. So do you have any doubt from last class to anyone of you?
No, sir.
No, sir.
So, which part of India are you from?
I am from New Delhi.
All right. Because of the cold, you know.
Yes,
I assumed it's very cold there.
too much chill. Day before yesterday, it was around 7 degrees Celsius. Okay. So in last class, I defined you expansion of particular solid in one-dimensional, two-dimensional, three-dimensional. That is linear expansion, aerial expansion, volumetric expansion. Next, we have to define temperature dependency or varying density. Let's say at low temperature, at temperature T naught, volume will be V naught. So according to the formula, density equals to mass divided by volume. So we can write rho equals to mass divided by volume. On changing temperature, there will be change in dimension of object, but mass of substance remains constant. So we can say mass remain same. So on temperature T, volume will become V naught 1 plus gamma delta T according to expansion. So from this relation, we may find density. Density at some temperature T equals to mass divided by volume. Put the value of volume to be V naught times 1 plus gamma delta T. So you'll get M divided by V naught 1 plus gamma delta T. Now this particular quantity, mass divided by volume, is nothing but rho naught according to this above relation. So we can write it as rho naught divided by 1 plus gamma delta T. Is it clear?
Yes, sir.
Yes, sir.
Now, in this particular denominator, since 1 plus gamma delta T raised to 1, so if you move to numerator, its exponential will become negative. So rho equals to rho naught 1 plus gamma delta T raised to minus 1. Now, according to binomial expansion, 1 plus x raised to n, we can write it as 1 plus n times x. So this exponential minus 1 would get multiplied with this gamma. So it will become rho naught 1 minus gamma delta T equals to rho. So from this relation, we can conclude on increasing temperature, since we have negative sign at this part, so it will tend to decrease it. So on raising temperature, density of object decreases. Is it clear?
Yes, sir.
Yes, sir.
Okay, just write it down. You all have written?
Yes, sir.
1 minute, sir. Done, sir.
If density of mercury at 0 degrees Celsius is 13.6 gram per centimeter cube. Find its density at 50 degrees Celsius if temperature coefficient linear expansion is 2 into 10 to the power minus 4 Kelvin inverse. Try to find using the above expression.
The temperature can be in Celsius, right? No need to change it to Kelvin.
I defined in last class, difference in temperature in Kelvin as well as Celsius both will remain same.
Yes.
So you don't need to convert it. Just see that. Change in Kelvin equals to change in Celsius. So you don't need to convert it.
Okay.
Gautam and Sham, please check your answer.
Okay.
Here we have given temperature coefficient of linear expansion. But according to relation, density is related with this gamma, which is volumetric expansion. So first you have to convert linear expansion into volumetric expansion, then apply the formula.
Okay.
Krishna, just check your calculation. On increasing temperature, density will decrease. Good, Gautam. Raza, just send me your answer. Minashi, Minashi, just check your calculation. We have to calculate final density. Raza, just see this particular formula. There is negative sign. So you have to subtract.
Okay, sir.
Let me solve. We have initial temperature 0 degrees Celsius, final temperature 50 degrees Celsius. So delta T will be 50 minus 0, that will be 50 degrees Celsius. Initial density is 13.6. Alpha is 2 into 10 to the power minus 4 Kelvin inverse. So gamma will be 3 times of alpha. So it will become 6 into 10 to the power minus 4. So rho equals to rho naught 1 minus gamma delta T. Rho naught is 13.6. 1 minus gamma is 6 into 10 to the power minus 4 multiplied by change in temperature 50. So 13.6, 1 minus 6 into 5, 30 or 300. So it will become 0.03. So 13.6 into 0.97, just multiply it. So it will become 13.2 gram per centimeter cube. Is it clear?
Yes.
Yes, sir.
Nabila, any doubt?
No doubt.
You all have written?
Yes, sir.
Yes, sir.
Mazia?
Yes, sir.
Okay. But there is exception for this particular formula in case of water. So we may define anomalous behavior of water. Let's say this is volume versus temperature. Density versus temperature. So first, on going from 0 degrees Celsius to 4 degrees Celsius, volume of water decreases and density increases, which is opposite of this above relation. So there will be exception for water for this particular case. So if you plot variation of volume and variation of density for this part, let's say so on going from 0 degrees Celsius to 4 degrees Celsius, density will decrease, volume will decrease, and density will increase to its maximum. But on going further above 4 degrees Celsius and above, volume increases and density start decreasing. So it will start to go upward and to go downward. Is it clear?
Yes.
Yes, sir. Yes.
This behavior and
So the line is 4 degree, right?
this particular temperature is 4 degrees Celsius. So we are considering this part and this part. Before 4 degrees Celsius, or you can say from 0 degrees Celsius to 4 degrees Celsius, it is exception according to the above formula in case of water only. And that will be due to we have in water hydrogen bonding, which may behave differently in between this particular temperature range. Is it clear?
Yes.
Now, related to this part, suppose temperature of surrounding is less than 0 degrees Celsius or at 0 degrees Celsius. So formation of ice will start from surface. And below this particular surface, water will have temperature greater than 0 degrees Celsius. So they will remain in liquid state, and which will facilitate for survival of aquatic life just below this particular sheet. And this ice on the surface of water will act as shielding to that aquatic life. Is it clear?
Yes, sir.
Okay, just write it down. Do you all have written?
One second, sir. Done.
Raza, done?
Yes, sir.
Let me ask you conceptual question related to this part. Heating of liquid in vessel. Suppose you have a vessel placed on burner and in this vessel, suppose liquid is filled up to this point, let's say A. So you'll be asked on heating, how will level of this liquid change? Will it increase or decrease? I'm just considering before its evaporation. How will level of liquid in this particular vessel may vary on increasing temperature?
It will increase.
Okay, the most obvious question answer. Okay, anyone more? If you think level of liquid decrease,
Like while it's heating, it increases. And after that, it will decrease.
okay. Minashi,
Yes, sir.
you'll go with that answer or you want to change in answer?
After heating, a little decrease.
After heating, it will decrease due to evaporation of liquid.
Yes.
We are considering there is no evaporation in this particular liquid. So what will happen? Will the level of liquid increase or decrease?
Increase.
Okay. Raza, any different answer? Okay, let me give you some hint. On heating, which of these two will receive heat first? Vessel or liquid? Mazia,
The
vessel.
vessel.
So everything on heating get expand except water. We are not considering water having temperature 0 degrees Celsius, 4 degrees Celsius. Okay, on heating, this vessel will expand. And expanding this vessel, volume of vessel will increase or decrease? Volume of vessel will increase. Hence, level of liquid first decreases. Is it clear?
Yes.
So why doesn't the liquid get the heat to? The heat is transferred from the container onto the liquid, right?
Which one will receive heat first, vessel or liquid?
At first, the vessel.
Vessel. So everything on heating get expand. Since vessel get received heat first, so it will expand first, and hence volume of lip vessel will get increased and level of liquid initially get decreased. And then afterward, on transferring heat or due to conduction of heat through this particular vessel, which is transferred to this liquid, which will tend to increase its volume, hence level of liquid start rising up. Is it clear?
Yes, sir.
So we can say in this part, level of liquid in this vessel first decreases to this point B, due to expansion of vessel, and then it will increase to this point due to its own expansion, let's say C. Nabila, is it clear?
Can you explain once again?
Okay. In this part, on placing this entire thing on this burner, since this vessel and this liquid or this particular system, on placing on this flame, vessel will receive heat by this flame first, and on absorbing that amount of heat, it get expand. So volume of vessel will increase, which will tend to decrease the level of liquid in it. Now, after it, heat will conduct through this particular vessel to reach this liquid, so which may start heating up and then its level increases. So initially, level of liquid decreases due to expansion of vessel, then increases due to its own expansion.
Okay, sir.
Is it clear to everyone?
Yes, sir.
Yes, sir.
So we can say on heating, since vessel will receive heat first and get expanded, so level of liquid decreases. Then, due to its own expansion, so if you have to define the relation between these three different terms, A, B, AC, and BC, so we can write BC equals to AB plus AB, AB plus AC. BC is actual expansion or real expansion of liquid. So we can say a real expansion of liquid is equals to AB, which is expansion of vessel, plus AC, which will observe to be, or we can say apparent expansion. Minashi, is it clear?
Yes, sir.
Okay.
Why is it called apparent expansion, sir?
If initially, if you could not absorb this particular term from starting to any particular end, let's say if you place it and go somewhere else, and then on returning back, you will see there is level from this point to this point. So falsely, it will be observed from this point to this point. So we can call it as apparent expansion. In general, it is going from this point to this point. Is it clear?
Okay, sir. Okay, sir.
You all have written?
1 minute, sir.
Yes, sir.
Done, sir.
You all have written?
Yes, sir.
So this is all about expansion and its various application. Next. Calorimetry. Let me define you what you mean by calorimetry. Calorimetry is simply exchange of heat between any two body or system, which results in two different parts. First, it will responsible for changing temperature or change in state of that particular object. So calorimetry is simply the study of exchange of heat between two body or system, which result in change in temperature or state. So according to conservation of energy, if there is no loss of energy in surrounding, if there is no loss of heat in surrounding, then according to principle of calorimetry, we may write heat lost by one body must equals to heat gained by another body. This is called principle of calorimetry. According to conservation of energy. Is that clear?
Yes, sir.
Jaza, any doubt?
No, sir.
Now, for this particular heat, we have two different cases. First, which result in change in temperature, and second, change in state. So we may define this into two parts: heat, which causes to change in temperature, and second, heat, which causes to change in state. Heat, which is responsible to change in temperature, may be of three different types. First is called heat capacity. Second, specific heat capacity or constant. And third, molar specific heat capacity. I will define you each the three terms. Second, heat, which causes the change in state of body. So first will be latent heat of fusion. You must have learned about it in your class 9th.
Yes.
Similarly, latent heat of vaporization. So latent of fusion is changing state from solid to liquid, and latent of vaporization is change in state from liquid into vapor. First, write it down to this part, then I'm defining you each term.
Done, sir.
One minute, sir.
Done.
Done, sir.
So first is heat capacity. It states amount of heat is required to raise or change temperature of any particular substance by 1 degree Celsius or 1 Kelvin. The amount of heat first, I will define you or definition part of this entire 5 different topic. Then I will define you how to apply for different problems. Okay. So heat capacity is the amount of heat is required to change the temperature of any substance by 1 degree Celsius or 1 Kelvin at normal atmospheric pressure. So Q equals to heat capacity constant S times change in temperature. So this S is called heat capacity. So SI unit related to this formula will be joule per Kelvin or per degree Celsius. Next, in this particular part, if there is mass or if we are calculating heat for fixed amount of mass or fixed amount of substance, it is called specific heat capacity or constant. So it will be the amount of heat is required to raise the temperature of 1 kg substance by 1 Kelvin or 1 degree Celsius at normal atmospheric pressure. I will define you later impact of atmospheric pressure on these quantity. So Q equals to mass of substance times specific heat constant times change in temperature. So this small s is called specific heat capacity. So it's SI unit joule per kg per Kelvin. Now, for calculation purpose, you must remember some of term. First is specific capacity for water. It will be 1 calorie per gram per Kelvin. 1 calorie equals to 4.186 joule. Similarly, specific capacity for ice and specific capacity for vapor equals to 0.5 calorie per gram per Kelvin. Is it clear?
Yes,
Sir,
sir.
Yes.
this is small s, right? The specific heat capacity is small s, right?
Yeah. Capital S
Another
heat capacity, small s specific heat capacity.
specific capacity is small s.
Yeah.
Okay.
In this part, we are considering any solid object or any liquid object. But suppose if you have to calculate this particular amount of heat in terms of or for gas, we may define amount of substance in terms of mole. So you can call it as molar specific heat capacity. So this will be the amount of heat is required to raise the temperature of 1 mole gas through 1 degree Celsius or 1 Kelvin at given condition. Since this molar specific constant may get changed according to different condition of gas, I will define you in thermodynamics. We mainly have 4 different types of processes. One is isobaric, isochoric, isothermal, adiabatic. So depending upon different given condition, this molar specific heat constant will have different numerical value. Okay?
Yes.
Sir,
Yes, sir.
Yes.
so shouldn't a specific heat capacity of ice be more than water, more than vapor? Because the distance they're more strongly bounded, right?
No, we are
No.
calculating amount of heat required to raise its temperature only. So the numerical value of
Not
these
to
two terms
change.
is same. So in
Okay.
case of latent heat, it will be different.
Okay.
So
But
in
wouldn't
this,
ice need more power to raise the temperature? Since
no,
it's a
no,
solid.
no. Numerically, the specific heat for both these two terms are same. For water, it will be maximum.
Okay.
So Q equals to number of moles times molar specific constant C times change in temperature. So this C is called molar specific heat capacity. So we have 3 different heat to change temperature of given substance. So if you relate these 3 quantity, we may write it as capital S equals to mass times small s equals to number of moles times molar specific constant. In this part, n is number of moles. We may be written as given mass divided by molar mass. So if you have to convert from one part to another, just use this formula. Okay.
Yes, sir.
Sham, any doubt?
Yes, sir. Yes.
First, write it down till this part.
So in the second equation, m is mass, right? M equals mass.
Yeah.
So can you scroll down?
Done, sir.
Mazia, done?
Yes, sir.
Yusra?
Yes, sir.
Okay. The next part, heat, which is responsible for change of state. So first is latent heat of fusion. So it will be the amount of heat is required to change 1 kg solid into liquid at normal atmospheric pressure and melting point. So Q equals to mass of substance times latency of fusion. You may say this particular term as the amount of energy evolved on converting from liquid into solid at its melting point and normal atmospheric pressure. Okay. This L is called latent heat of fusion constant. And for ice, it will be equals to 80 calorie per gram. In case of converting from liquid into vapor, it is called latent heat of vaporization. Latent heat.
Sir,
Yes.
sir, I don't see how multiplying mass with latent heat of fusion will give us Q.
Just see the unit. L equals to L having unit calorie per gram. Okay.
Okay.
So gram is unit of
And then
mass. So gram.
Okay. Got it.
I'm calculating in terms of calorie. It will be easier to remember. Okay. Latent heat of vaporization. The amount of heat is required to change 1 kg liquid into vapor at its boiling point and normal atmospheric pressure. So Q equals to mass of substance times latent heat of vaporization. So this LV is called latent heat of vaporization constant. And in terms of water, to convert into vapor, it is equals to 540 calorie per gram. Okay, Gautam?
Yes. Sir.
Just write it down to this part. I'm giving just 2-minute break, okay? Okay. You all have written to this?
Yes, sir.
Yes, sir.
Yes.
Now, this particular latent heat of fusion and this latent heat of vaporization. Gautam, just tell me why it is called latent?
Because the temperature doesn't change.
Why?
Because when we actually see the experiment, we will think like where the heat is going on, because there's no change in the state, there's no apparent change in the system, but still the system is absorbing the heat. It's like
Okay.
hidden.
It is basically due to on applying heat to that system, it get utilized in breaking of bond to convert it from one state to another. Then that's why there will be no change in temperature. It will remain same. Okay. So it is called latent heat or hidden heat. Is it clear?
Yes, sir.
Now, depending upon these different 5 factors, let me define you how to simplify or solve any problem. For that, let me give you a graph or define your graph. This vertical line, temperature, and this horizontal line, heat supplied. Suppose you have ice at minus 10 degrees Celsius. So it will be at this point. So on giving heat to this ice, it will tend to change in temperature from minus 10 degrees Celsius to 0 degrees Celsius, like this. So this amount of heat given to this ice will be termed as specific heat, since in this part, temperature of substance or ice is changing. So it will reach to this point, 0 degrees Celsius. Now on further heating, state of ice will start to change from ice to water. So it may convert it into water. Till that point, there will be no significant change in temperature. So this curve will not go up or go down. So this particular heat given to this ice to change its state is called latent heat of fusion. On further giving heat, temperature of ice will start increasing till this point. Hundred degrees Celsius. On further heating, it will start to change its state from water to steam. So initially, it will be in terms of water or in state of water. Now it gets converted into vapor. So this will be termed as latent heat of vaporization. From water 0 degrees Celsius to water 100 degrees Celsius, it will be capable of changing its temperature. So we can call it as specific heat. And further, along this way, it will tend to increase the temperature of vapor to any higher temperature as well. So do you have any doubt in this particular curve?
No, sir.
Minashi?
No, sir.
Okay. So first question related to this graph will be how the slope of a specific heat in this particular curve will relate it with one another. Let's say inclination of this particular part, theta 1, this particular curve, theta 2, and at this particular curve, theta 3. Gautam, any idea what this
The
particular
slope
theta
is
actually
small.
defines?
No. It's maybe temperature by heat. That is
Good. So for calculating this particular theta, vertical line is temperature and horizontal line is heat. So let me define you a formula related to these two terms. We can write heat supplied to this particular system to change its temperature is called specific heat. So we can write it as mass of substance, a specific heat constant times change in temperature. Now move this dq to right side and m into s to left side. So it will be 1 by m into s equals to dt by dq. So this particular ratio, dt is in perpendicular and dq is in base. So perpendicular divided by base will be termed as slope of this particular curve. And now, according to this relation, this slope is inversely proportional to this s, which is nothing but a specific heat constant for that particular substance. Is it clear?
yes, sir.
Sir, can you please explain this once more?
Since in these three different straight line or this inclined line will simply define to you heat supplied to that system to change its temperature. So which is called as specific heat. So Q equals to ms times change in temperature. So I've written dq equals to m into s times dt. Now, since this particular curve is in between temperature and heat, so vertical line is temperature and horizontal line is heat. So keep temperature to be in numerator and heat to be in denominator. So I have rearranged this particular equation like this. So we can say dt by dq simply defines you perpendicular by base, which is nothing but tan theta, or it will be termed as slope. And this slope, according to this relation, is related to inversely proportional to a specific heat of that substance. Is it clear?
Yes, sir.
Now, I've given you different values
So
per specific heat, yes.
so theta 1 and theta 3 should be equal, right? Since the specific heat of both ice and vapor are
Just
same.
see. We have specific heat capacity for ice and vapor is same. So slope of ice curve and vapor curve will have equal inclination. And specific capacity of water is 1 calorie per gram per Kelvin, which having more value or numerical value. So it will have lesser slope or lesser inclination. So from this, we can conclude theta 1 and theta 3 should be equal to each other and it will be more as compared to theta 2. So we can write since specific heat capacity for ice equals to specific heat capacity for vapor and it is smaller as compared to water. Therefore, theta 1, theta 2 are equal and it will be greater than theta 3. Is it clear?
So 1 and 3 should be equal, right?
Which part?
1 and 3 should be equal, right? And should be
Okay, just 1 minute.
greater.
Mazia, is it clear? Okay. Next question will be, Suppose you have water and steam at same temperature 100 degrees Celsius. So which will be more effective or which will cause more severe burn, water or vapor?
Vapor.
Similarly, ice and water at same temperature 0 degrees Celsius. So which will be more effective in cooling?
Ice.
So according to this graph, we may define these two terms as well. Suppose if you draw a vertical line, so just see which among these two terms having more amount of heat, vapor or water.
Vapor.
Vapor.
So vapor will cause more severe burn than water at same temperature. Similarly, at this point, ice and water at same temperature 0 degrees Celsius, which will have more amount of cold energy, water or ice?
Ice.
Ice.
Ice. So ice will cause more effective cooling as compared to water at same temperature. Is it clear to you all?
Yes, sir.
Yes, sir.
Yes.
So just remember, according to this particular graph, water and ice at 0 degrees Celsius, ice will be more effective in cooling. Similarly, water and vapor at 100 degrees Celsius, vapor will cause more severe burn. Just write it down to this part first. Draw this graph.
So 1 second, sir. Upstairs. You can show the graph 1 second.
Okay, just one.
Done.
You all have done?
One sec. Done.
Minashi, any doubt?
No, sir.
Yusra?
Yes, sir.
Okay. Now let me define you how to solve any problem. If 10 gram ice at minus 20 degrees Celsius is mixed with 10 gram water at 10 degrees Celsius. Find resulting temperature and their amount. Let me give you some hint how to simplify it. For any problem, first draw graph related to that part. So in this term, we have two different parts. One is ice and the other is water. Temperature versus heat. Ice is at minus 20 degrees Celsius at this point. So on giving heat, its temperature would change from minus 20 degrees Celsius to this 0 degrees Celsius. So it will be termed as specific heat. Similarly, for water, initially it is at plus 10 degrees Celsius at this point. So on getting mixed with ice, some of its heat may get loose. So it may acquire this particular temperature by losing some amount of energy, let's say Q1. Is it clear till this part?
So even the water becomes 0 degrees Celsius.
No, we are just considering initial case for ice to go from minus 20 degrees Celsius to 0 degrees Celsius and for water to go from 10 degrees Celsius to 0 degrees Celsius. Now calculate
Just
Q1.
considering. Okay.
Yeah, Q1 is specific heat. So it will be mass of ice, specific capacity of ice, change in temperature. Similarly, capital Q1 is mass of water, specific capacity of water, and change in temperature. Just put the value of these two terms and simplify it for Q1 and Q2. Try to solve.
So what will be SI and SW?
SW is specific heat capacity of water.
Yes, yes, yes.
So it would be +1. Try to calculate in terms of gram. So your answer for Q will be in terms of calorie. Please ask if you have any doubt in calculation of these two terms. Mazia, any doubt? Raza?
What I'm doing.
Okay.
Sir, will SI and SW be in negative or positive?
Temperature difference will be always positive. So take 0 degrees Celsius minus 20 minus minus plus.
Yes.
So it will be plus 20 degrees Celsius. Minashi, is it for small q1 or capital Q1?
For both.
Good. Good at Sham. Good Krishna. Mass of ice is 10 gram. Specific capacity of ice is 0.5. And change in temperature is 20. Final temperature minus of minus 0, 20, it will be plus 20. So on simplifying, you will get 100 calorie. Similarly, for second part, that is for capital Q1, mass of water is 1, specific capacity of water is 1, and change in temperature is 10. So you'll get 100 calorie. Now, above 0, this particular amount of energy, capital Q1, will be termed as heat energy. And below 0, this amount of heat will be termed as cold energy. Now, since the numerical value of these two parts are equal, so we can say heat lost by water on going from 10 degrees Celsius to 0 degrees Celsius equals to heat gained by ice to go from minus 10 degrees, minus 20 degrees Celsius to 0 degrees Celsius. Now, there will be no any amount of energy left out in this particular system, which will tend further to convert state from one part to another. So these two terms will be remains as it is at this particular point in its equilibrium. So ice will remain at 0 degrees Celsius and water will remain at 0 degrees Celsius, having same amount 10 gram and 10 gram each. Is it clear?
So can you repeat?
Since in this part, we have 100 calorie lost by, or it must be required by ice to go from minus 10, 20 degrees Celsius to 0 degrees Celsius. So we may call it as cold energy. Amount of heat lost by water on going from plus 10 degrees Celsius to 0 degrees Celsius is also 100 calorie. So we may call it as heat energy. So if you combine these two terms, this amount of heat energy and this amount of cold energy will cancel out each other effect. So there will be no excess amount of heat or cold energy left out from in this particular system. So ice will tend to remain at ice at 0 degrees Celsius and water will tend to remain at water at 0 degrees Celsius. Is it clear?
Yes, sir.
Yes.
Sir,
Yes.
but we had taken 0 degrees Celsius as a reference point in the beginning of the question, right? What if we take some other point?
I've
Then
just
calculate the heat
initially
required.
taken amount of heat lost by water to go from one state to another state. Let's say after this
Okay.
particular 0, it may get start to change state. So we are considering first at this particular term to be initial state or just a starting reference. If there will be further more enough energy in this particular system, so this quantity may get changed from one part to another. Okay, let me give you another problem related to this part, which may have some different amount of energy. So in this point, we can say mass of ice and mass of water will remain 10 gram each, and at equilibrium, temperature of this particular system will be 0 degrees Celsius. Raza, is it clear?
Yes, sir.
If 100 gram ice at 0 degrees Celsius is mixed with 100 gram vapor at 100 degrees Celsius, find the resulting temperature and their amount. According to this question, we have initially 100 gram ice at 0 degrees Celsius. So it may be at this point, ice. So first, it will require to change its state from this point to this point to convert into water. So this will be small q1. And then if this particular system will have more amount of heat energy, then it will further tend to move from this point to this point to raise its temperature up to 100 degrees Celsius. So it will be Q2. And if it would have further amount of heat energy, that will tend to convert into steam. Let me stop at this part. Now for steam, initially, it would be at this part. So it may lose some amount of energy to go from vapor to water. So let's say this is capital Q1. So first try to find small q1 and capital Q1. So a small q1 will be latent heat of fusion to convert ice into water. Capital Q1 is latent heat of vaporization to convert vapor into water. So according to this, we can write Q1 equals to mass of ice times latent heat of fusion. Just calculate this. Similarly, capital Q1 is mass of vapor times latent heat of vaporization constant. First, write it down and try to solve these two parts as initial reference or initial guess.
Sir,
Yes,
in the previous question, what was the answer for the resulting temperature?
0 degrees Celsius.
Okay, yeah.
Since at 0 degrees Celsius, there will be no enough cold or heat energy left out in that system, which will tend to convert one state to another. Okay.
Yes, sir. So it will be 8,054,000, right?
Since we have mass of ice, 100 gram, latent heat of fusion constant is 80. So it will become 8,000 calorie. I think you all have got this particular part. Similarly, for vapor to condense from vapor to water, mass of vapor is 100 and latent heat of vaporization constant is 540. So it will be 5400 calorie, means 54,000 calorie. Is it clear?
Yes, sir.
Yes.
Now, which of these two have more amount of energy?
The Q1, the capital Q1.
So we can say we have more amount of heat energy as compared to cold energy. So further, this ice will rise or raise its temperature from 0 degrees Celsius to reach at 100 degrees Celsius water. So we may calculate Q2 also. So Q2 will be equals to mass of ice times, now it have converted into water, so it will be the specific heat capacity of water times change in temperature. Ice having mass 100 gram, specific heat of water is 1, and change its temperature will be from 0 to 100, so it will be 100. So on simplifying, you will get 10,000 calorie. Is it clear?
So it will be calorie per gram, right? In this.
No, we are calculating energy, so it will be in terms of calorie.
Okay.
Is it clear to all till this part?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Now, if
So
you add
Q1,
these two
Q2,
terms,
and those are all along the x-axis, right?
yeah, it means we have reached up to this part. So total amount of this at this part is 100 gram ice and 100 gram vapor. So we have total 200 gram of water and still having some amount of heat energy in this particular system. Let me simplify it. If you add these two terms, you will get 18,000 calorie and we have 54,000 calorie heat energy. So this 18,000 calorie will be cold energy and 54,000 calorie heat energy. So if you subtract these two terms to get net amount of heat energy left out in this particular system after this arrangement. So Q net will be equals to 54,000 minus 18,000. So it will be 36,000 calorie. Is it clear?
Yes, sir.
Yes.
Yes, sir.
Now, this amount of heat energy, which is left out in this particular system, which will tend to convert some amount of water into vapor. So let me calculate mass of water that will tend to convert into vapor due to this amount of heat energy. So some amount of water will convert into vapor. So according to the formula, Q equals to M into LV. So M equals to net amount of heat energy divided by latent heat of vaporization constant. Net amount of heat energy we have 36,000 calorie. Net amount of or latent heat of vaporization constant is 5,400, 540. So this zero will cancel out. 18,3, 18 twos are. So it will be 66.7 gram. In total, we have 100 gram plus 100 gram, 200 gram of water. Now, from that part, 66.7 gram will convert into steam and we're left with 133.7 gram. So in total, we can write water will be 200 minus 66.7. So it will be 133.3 gram, and vapor, it will be 66.7 gram, and their resulting temperature will be 100 degrees Celsius. Is it clear to you all what I have done?
Yes.
Nabila?
Clear, sir.
So why is the resulting temperature always steam point or ice point? Why not any intermediate temperatures?
Due to its amount and amount of heat energy and cold energy in this particular system. What I have done in
There
this
can be
particular part,
cases.
Yeah, they can be. In this, since we have vapor, so first I have calculated this amount of heat energy, which may be evolved on going from vapor to water. So this will be about 54,000 calorie. On converting ice from this part to this point, it would require just only 8,000 calorie, which is very small as compared to this part. So it may get converted to water. So it will require this much amount of heat energy. So in total, it would just require 18,000 calorie heat from this vapor. But still, we have in this particular system 36,000 calorie heat left out. This much amount of heat energy will tend to convert some amount of water into vapor, which I have calculated this. So in total, water will be 133.3 gram and vapor will be 66.7 gram and resulting temperature will be at 100 degrees Celsius. Is it clear?
Yes, sir.
Yes, sir.
Okay, just write it down.
Done, sir.
Done. Done, sir.
You all have written?
Yes.
Yes, sir.
Yes, sir.
Okay, so let's stop here for today. In next class, I will define you some problem related to this part. Then we'll start heat transfer from one part to another using three different ways: convection, conduction, and radiation. Okay, the last part of this particular chapter.
Okay.
Okay, then we'll continue next class.
Thank you, sir.
Thank you.
Thank you.
Thank you.